Welcome to the new concept of insulation of steam generators. As you know that we were discussing about the various aspects of steam distribution network with different accessories and mountings attributed to boiler house, etc. Now, when we talk about the steam generators, the insulator is a very prominent phenomena. Now, before we go into the detail, let's have a look at what different kind of topics we covered previously. We discussed about the concept of water for boiler. Then we discussed about the water carryover. We had a discussion about the external water treatment protocols. Under the edges of accessories and mountings, we discussed about the safety valves and its selection, how different type of safety valves can be used, what are their material of construction, how you can select the appropriate one. We discussed about the seating reseating concept for safety of the boiler. Condensate is an extremely important part of any steam distribution network and steam generation aspect. We discussed about the condensate recovery concept. In this particular lecture, we are going to discuss about the insulation aspect of steam generators. We will discuss about the various design equations attributed to the thermal insulation, and to support all these things we will discuss a couple of numerical problems. Now, when we talk about the insulation, so all hot surfaces at temperature above 333 Kelvin must be insulated for personal protection. It is not only ensure the personal safety or the person, those who are working around that particular surface must be safe, but also it ensures that the thermal efficiency of the system must be secured properly. The thickness of insulation is usually chosen to ensure a maximum external surface temperature of 328 Kelvin for metal surface and 333 Kelvin for non-metallic surface. In addition to personal protection, insulation is also applied to flue gas path and flue gas ducts to ensure the flue gas temperature entering the chimney remains above its acidic dew point to prevent the low temperature gas corrosion. Now, this particular concept is again very important, because if it is below the acidic dew point, then the condensation may take place, and whatever the condensate product, they may have a corrosion aspect, and it can create the problem to the system. Apart from this, due to the environmental issues, you need to maintain the appropriate temperature so that all the flue gases must acquire the exit path properly. Additionally, thermal insulation is applied to a steam generator to ensure the steam is supplied to its point of application at the correct temperature without any drop. Now, there are various heat traced piping and vessels. They are also applied with insulation to ensure maximum transfer of heat and minimum heat loss from surface. Now, when we talk about the thermal insulation, obviously we cannot overlook the importance of thermal insulation materials. There are 4 types of thermal insulation materials: granular, fibrous, cellular, and reflective. Now, the granular materials such as calcium silicate, they contain air entrained in the matrix. So, this acts as the insulating material. Fibrous material such as mineral wools, this contain air between the fibers. Now, third category is the cellular materials, that is a cellular grass and a foam plastics. This contain small air or gas cells sealed or partly sealed from each other. They are reflective insulation materials. This consists of numerous layers of spaced thin sheet metal materials of low emissivity, such as aluminum foil, stainless steel foil, etc. In practice, a combination of two or more of the above four types are being used. Let's talk about the properties. Now, heat from hot surface is transferred or lost through an insulating material to the surrounding area either by radiation and or by convection. Thermal insulation should limit the heat loss to a minimum one. The main requirement of thermal insulation material is low thermal conductivity. Since heat is transferred through insulating material by conduction at 373 Kelvin, thermal conductivity of say mineral wool is 0.047 watt per meter Kelvin. That of glass fiber, it is 0.038 watt per meter Kelvin. Of calcium silicate is 0.057 watt per meter Kelvin, and of magnesia it is 0.062 watt per meter Kelvin. Thermal insulation material should have the following properties to ensure the satisfactory performance of the material for the life of a plant. Now, this is again a very, you can say, the important thing, because it should possess, because any material cannot possess the property of thermal insulation. So, there must be some requirement, compatibility with the process. Now, the material must be suitable for continuous use at maximum operating temperature without degradation to its physical properties. It must be non-corrosive to plant and pipe work if wet by rain or leakage of water, either steam. It should not be permanently damaged if contaminated with water. It should have adequate compressive strength to resist local loads such as foot traffic, ladders, etc. It must have adequate flexural strength and impact resistance to permit transportation and application without breakage. Material must be non-combustible. It should not cause any discomfort or health hazard to the operating person. It should be tight, free of voids and well anchored. Now, removal and replacement, it should be required only during the maintenance or modification of plant. Now, let us talk about the design of thermal insulation. From basic heat transfer theory, it is known that under steady state condition, the heat loss from a hot flat surface through thermal insulation to the ambient air is usually expressed as Q is equal to Th minus Tc upon L by K, that is equation number 1. Here Q is heat loss in watt per meter square, Th is the temperature of hot surface in Kelvin, Tc is the temperature of ambient air in Kelvin, L is the thickness of insulation in meter, K is the thermal conductivity of insulator in watt per meter Kelvin. Another equation is that Q is equal to Tc minus Ta into F. Now, where F is the surface coefficient of insulating material having the unit of watt per meter square Kelvin. Now, if we combine these two equations, we will get Q is equal to Th minus Ta upon L by K plus 1 by F, and that is equation number 3. Now, the temperature of cold surface or the surface of an insulation material can be calculated by rearranging this equation number 2. So, it is Tc is equal to Q upon F plus Ta, and that is equation number 4. Now, for steady flow of heat through composite walls, that is wall of a vessel lined with thermal insulation, we can represent this equation number 3 as Q is equal to Th minus Ta upon L1 by K1 plus L2 by K2 plus 1 upon F, and that is equation number 5. Now, where L1 is the thickness of wall in meter, L2 is the thickness of insulation in meter, K1 is the thermal conductivity of wall material, W by M meter Kelvin, K2 is the thermal conductivity of insulator in watts per meter Kelvin. Here, this one. Now, the expression of cold surface temperature Tc will remain same as per equation number 4 here. Now, the heat loss from the insulated cylindrical surface, that is pipe, tubes, small diameter vessels, this can be written as Q is equal to Th minus Ta upon Ri into ln R naught upon Ri into 1 upon K Ri upon R naught into 1 upon F. Now, where Q is the heat loss in watt per meter square, Th is the temperature of hot surface in Kelvin, Ta is the temperature of ambient air in Kelvin, R naught is the outer radius of insulation in meter, Ri is the inner radius of insulation in meter, K is the thermal conductivity of insulator in watt per meter Kelvin, F is the surface coefficient of insulating material in watt per meter square Kelvin. The temperature of a cold surface or the surface of an insulation material can be calculated as Tc is equal to Q upon F into Ri upon R naught plus Ta, and that is equation number 7. For steady flow heat through composite cylindrical surface, we have Q is equal to Th minus Ta upon Ri upon K1 into ln Rc upon Ri plus Ri upon K2 into ln R naught upon Rc plus Ri upon R naught into 1 upon F, that is equation number 8, where Q is the heat loss watt per meter square, Th is the temperature of a hot surface in Kelvin, Ta is the temperature of ambient air, Ri is the inner radius of wall in meter, Rc is the outer radius of wall or inner radius of insulation in meter. R naught is the outer radius of insulation in meter, and this K1 is the thermal conductivity of wall in watt per meter Kelvin, and K2 is the thermal conductivity of insulation in watt per meter Kelvin, whereas F, this F is the surface coefficient of insulating material in watt per meter square Kelvin. Now, the expression of cold surface temperature Tc remains the same as per the equation number 7. Now, let us talk about couple of numericals problem. Now, for the problem number 1, the hot surface temperature of 150 millimeter thick wire brick wall is maintained at 1088 Kelvin. Now, if the average thermal conductivity of the wall material is 0.196 watt per meter Kelvin, you need to determine the maximum heat loss through the wall to ensure its cold surface temperature does not exceed 333 Kelvin for an ambient air temperature of 294 Kelvin. What is the surface coefficient of the wall material? Let us have the solution. Now, we can use the heat loss equation. Q is equal to Th minus Tc upon L by K, where Q is equal to heat loss in watt per meter square, Th is equal to temperature of hot surface in Kelvin, Tc is the temperature of ambient air in Kelvin, L is the thickness of insulation in meter. K is the thermal conductivity of insulator in watt per meter Kelvin. Now, the maximum heat loss through the brick wall may be determined as Q is equal to 1088, that is supplied, minus 333 upon 0.15 0.196, and that comes out to be 983.53 watt per meter square. This is the first part of the answer. Now, the surface coefficient of the wall material can be found from equation, that is Q is equal to Tc minus Ta upon F, where Ta is temperature of cold surface in Kelvin and F is the surface coefficient of insulating material, and that is watt per meter square Kelvin. So, F is equal to 983.53, which is calculated, upon 333 minus 294. The desired one is 25.296 watt per meter square Kelvin. This is the desired result. So, now let us discuss about the second problem, and second problem that is attributed to the similar type of thermal insulation. Now, steam at a temperature of 623 Kelvin is flowing through a pipe with an outer diameter of 100 millimeter. The pipe is insulated with 20 millimeter thick mineral wool, the average thermal conductivity of which is 0.055 watt per meter Kelvin. You need to determine the outside surface temperature of mineral wool if ambient temperature is 300 Kelvin. You may assume the hot surface temperature of the mineral wool is the same as that of the flowing steam, and the value of the surface coefficient of the insulating material is 30 watt per meter square Kelvin. Let us discuss. The inside diameter of insulating material may be assumed to be same as the outside diameter of pipe. So, Ri is equal to 50 mm and R naught is equal to 70 mm. Now, we are having the equation Q is equal to T H minus Ta upon Ri into Ln R naught upon Ri into 1 upon K Ri upon R naught into 1 upon F, where Q is equal to, as usual, heat loss in watt per meter square, Th is equal to temperature of hot surface in Kelvin, Ta is temperature of ambient air in Kelvin, R naught is the outer radius of insulation in meter, Ri is the inner radius of insulation in meter, K is the thermal conductivity of insulator in watt per meter Kelvin. F is the surface coefficient of insulating material in watt per meter square Kelvin. So, Q is equal to 623 minus 300 upon 0.05 upon 0.055 into ln 0.07 upon 0.05 plus 0.05 upon 0.07 into 1 by 30. Now, if we calculate 323 upon 0.9091 into 0.3365 plus 0.0238, it comes out to be 979.64 watt per meter square. Now, the cold surface temperature of insulating material can be calculated by this equation. Tc is equal to Q upon F into Ri upon R naught plus Ta, and Tc is equal to 979.64 upon 30 into 0.05 upon 0.7 plus 300, and that is 323.32 Kelvin. This is the desired result. Now, let us take another problem that is again the last problem of this particular lecture, and that is one vessel having a carbon steel wall of thickness 10 millimeter is carrying saturated steam and water at 441 Kelvin. The vessel is insulated with the magnesia of thickness 50 millimeter. If ambient air temperature is 303 Kelvin, you need to determine the heat loss from the vessel. It is given that the thermal conductivity of the carbon steel is 52 watt per meter Kelvin. Thermal conductivity of the magnesia is 0.05 watt per meter Kelvin. Surface coefficient of the insulation surface is 10 watt per meter square Kelvin. Let us start. Now, assuming no temperature drop across the metal and applying the formula Q is equal to Th minus Ta upon L1 K1 plus L2 K2 plus 1 upon F, where L1 is the thickness of wall in meter, L2 is the thickness of insulation in meter, K1 is the thermal conductivity of wall material in watt per meter Kelvin, and K2 is the thermal conductivity of the insulator in wall watt per meter Kelvin. So, Q is equal to 441 minus 303 upon 0.01 divided by 52 plus 0.5 plus 1 upon 10, it comes out to be 151.83 watt per meter square, and that is the desired result which we are looking for. So, in this particular lecture, we have discussed about the thermal insulation of steam generators. We gave the importance of the insulation, we discussed the various type of insulation, we solved couple of numericals as an example, and if you wish to have a further reference, you can go for this particular reference for your convenience. Thank you very much.